So in the previous videos, we have proved two different properties of the norm in the case of Rn. Now we move on to the third property, which is N3. Okay, N3, the third property. The third property is norm of alpha x should be equal to modulus of alpha into norm x. This is what we have to prove. Okay, so here x is equal to, we written as theta 1, theta 2, etc. theta n. Okay, so alpha x should be equal to alpha theta 1, alpha theta 2, etc. alpha theta n. Okay, so moving on to norm of alpha x should be equal to, I use the modulus definition for this also, which is common for both real and complex numbers. That is square root of, my straight lines are not that straight, modulus of alpha theta 1 modulus the whole square plus alpha theta 2 modulus the whole square plus etc. plus alpha theta n modulus the whole square. Okay, so which can be written as summation j is equal to 1 to n modulus of alpha theta j the whole square and its square root. So this is what norm of alpha x actually means. Okay, now we can, modulus of AB can be written as modulus of A into modulus of B. So this can be written as square root of summation j is equal to 1 to n modulus of alpha into norm theta j the whole square. Okay, so which can further be implied that here it can be written as norm alpha square into norm theta j the whole square, and the summation j is invariant under alpha because the summation does not affect modulus of alpha. So we modulus of alpha square in fact. So we can take modulus of alpha square common outside. So this can be written as square root of modulus of alpha square into summation j is equal to 1 to n modulus of theta j the whole square, because modulus of alpha square is immaterial. So I use modulus because it can be used for both the real and complex numbers as well. That's why I use this argument. So now moving on. So this modulus of alpha square and its square root can be taken as modulus of alpha. Taking outside modulus of alpha into, so we have taken this thing outside, modulus of alpha square the whole raised to 1 by 2, which can be written as modulus of alpha into summation j is equal to 1 to n modulus of theta j the whole square and its square root. Now we already know that this is actually norm x by the definition. So this can be written as modulus of alpha into norm x. So this is what we have to prove. Norm of alpha x should be equal to modulus of alpha into norm x. So we have established our third property as well. So moving on to the fourth property. Fourth property is triangle inequality. So N4. For that we take an x. X is equal to theta 1, theta 2, etc. theta n. Y is equal to eta 1, eta 2, etc. theta n. Okay. So we have to find the value of norm of x plus y. For that, first we have to find the value of x plus y. X plus y is equal to theta 1 plus eta 1. Next is theta 2 plus eta 2, etc. theta n plus eta n. Okay, this is here it is comma. Okay, so this is what we have obtained. Okay, norm of x plus y should be equal to, the first component is theta 1 plus theta 1, second component is theta 2 plus theta 2. By our definition of norm x, we are squaring the modulus of each component and taking this taking the sum and taking the square root. This is what norm x actually means. So norm of x plus y should be equal to square root of summation j is equal to 1 to n modulus of theta j plus eta j the whole square, or summation j is equal to 1 to n modulus of theta j plus eta j the whole square, the whole raised to 1 by 2. Since we have already proved or proved our Minkowski's inequality, I won't be stating that inequality. So this is actually, this term can be written as, which is less than or equal to summation j is equal to 1 to n modulus of theta j the whole square, the whole raised to 1 by 2, and summation j is equal to 1 to n modulus of theta j, eta j the whole raised to 1 by 2. This inequality can be obtained using Minkowski's inequality. So then this first part is norm x, this second part is norm y. Here where x is equal to theta 1, theta 2, etc., theta n, y is equal to eta 1, eta 2, etc., eta n. So we can substitute the value of norm x and norm y. So norm x plus y should be less than or equal to norm x plus norm y. So norm x plus y should be less than or equal to norm x plus norm y. So we have proved all four properties. Okay, then we have enough to establish that our space Rn or Cn under this norm, you can substitute here modulus of theta I square as well, what are same, because in the real numbers case modulus of x the whole square and x square is same. So that's why I didn't use the modulus here. You can use the modulus and proceed in a similar way. So we have established the first property, the second property, the third property, and the fourth property. So we can clearly say that the space Rn and Cn under the norm, which is defined as such, is a normed space. So now I will be giving you some examples for you to prove. Okay, if you have any doubt regarding the proof of any of the examples which I am going to tell, you can certainly ask me and we can clarify. The first example is the space LP. So we have discussed about Rn and Cn. Now we are going to discuss about LP, the space LP. Okay, so LP consists of the element sequences which is defined as such, and LP is a Banach space, meaning it is a normed space with completeness property. Completeness property of this space has already been established, so the only thing you have to establish is it's a normed space. So before getting on to much things, so we have to define what is actually the norm. Here x is equal to sequence theta j, okay, with a sequence, then norm x should be equal to summation j is equal to 1 to infinity modulus of theta j raised to p the whole raised to 1 by, which is actually the norm which is defined. So we can easily prove this result because we have already established this result in the case of metric spaces. So similar arguments can be done. First argument is the norm x is greater than or equal to 0, which is same as in the metric space. And the second argument, norm x is equal to 0 if and x is equal to 0, which is as same as in the LP space. The third argument, you only have to substitute alpha, as in the previous case. Alpha, this thing becomes alpha x becomes alpha theta j. So alpha theta j the whole raised to p, take modulus of theta j outside, raised to p, the whole raised to 1 by p outside, then that becomes modulus of alpha. So the rest of the things becomes norm x, and the triangle inequality can be easily established using the inequalities which we have defined. So this is almost similar to what we have discussed in the metric spaces. So you have to prove that it's a normed space, and it also satisfies completeness property, which we have discussed in the case of metric space also. So it is same. And the third example is the space L infinity. I won't be proving any of this because you should be able to prove that. So this is also a Banach space. Okay, so here the norm x is defined as supremum j modulus of theta j, where x is equal to the sequence theta j. Okay, so here also we have proved this in the case of metric space. You are assuming the same properties and converting it into norm terms. That's what we are going to prove essentially. So I won't be discussing this as well. So next example is example number 4, which is also what we have discussed, the space CAB, set of all continuous function on closed interval AB, which is also a Banach space. Okay, here the norm x is equal to maximum t element of j x of t, modulus of x of t. Here we take the set of all functions from continuous function on closed interval AB, which should be bounded. Then we take the maximum of that function as norm x. In this case also we have established that it is a metric space. Use the same arguments, and to prove that it satisfies the normed conditions of the normed space, and its completeness was also established in the case of metric space. So I won't be discussing that as well. Example number 5 is the space of all continuous function on 0, 1, C0, 1. We have already discussed that here norm x is equal to integral 0 to 1 modulus of x of t dt. This is the norm, and actually this is an incomplete space. We have proved that in the case of metric spaces. Okay, so d of xy should be equal to modulus of integral 0 to 1 modulus of x of t minus y of t, okay, dt, which is actually norm x minus y. Okay, so this, using this metric, which is essentially the same norm, we have established that this is an incomplete space. So you have to prove that this is an incomplete normed space, that is completeness does not hold. That properties can be established from the incompleteness of a metric space. So this is an example of an incomplete normed space, and you have to prove that this is a normed space as well. So these 4 are your exercise problems for you to do. If you have any doubt, you can easily contact me. This is essentially same as in the case of metric spaces. We have proved the same condition in the case of metric spaces. The only difference is alpha x, and alpha x can be easily computed by elementary calculation. So I won't be discussing this for, you have to discuss this for, and I hope you understood. Thank you.